Hello. I'd like to take a few minutes and talk about the normal curve and z-scoring, the subjects of Chapter 5. Here you can see the normal curve on the board. We'll step back to Chapter 3 for a moment. You remember there we were in continuous variables. We were looking at collapsing the distribution to the center, some value in the center that best represented the central tendency of that distribution. And for the continuous variables, we were focusing on the mean and the median. We saw, and there is an illustration, figures 3.1, 3.2, and 3.3 in Chapter 3. We saw that where the mean and the median are approximately, either are the same or approximately the same, the distribution can be characterized as normal, taking a normal shape. In a situation where the mean is larger than the median, the distribution has a right-hand tail that's skewed and pulled positively to the right. Where the situation where the mean is smaller than the median, the tail is pulled to the left. We get a negative pull, negative tail. Remember, everything to the right of the mean, we've demonstrated that to ourselves, everything to the right of the mean is a value larger than the mean. Any of the x's to the left of the mean is smaller, so that if we subtract an x on the right-hand side, a mean from an x on the right-hand side, we get a positive value. Mean from an x on the left-hand side, we get a negative value. So anyway, we saw normal and skewed representations of curves in Chapter 2, or 3 rather. When we got to Chapter 4, and that illustration about response times to ambulance companies, we saw that it's possible to conceive of a normal curve that's flat, somewhat flat, and one that's more heaped. In other words, where we have a situation where more of the x's are clustered around the mean, where it's heaped, and more of the x's for the other alternative are spread out more towards spreading out to the tails, broadening out the shape of that bell. As we were in Chapter 4, that is the measure of dispersion. Measures of dispersion, we were focusing there on the standard deviation for the continuous variable. And we came to see it as an index of dispersion, an index of variation, a way of encompassing all of the variation in the distribution between the low and the high value. Remember, one thing that happened in Chapter 3, we collapsed to the center, and we lost all of that variation that was around the mean. We had a good value there, the mean, to compare one group against another. Somebody's, say, an age group that has a mean of 42, as opposed to another group that has a mean of 35, we'd say the age group of 42 is on average higher, right? Pretty obvious. But in the process of doing that central tendency, we lost all that variation of x's around the mean. Chapter 4, we get back and look at the dispersions, the variation around the mean, and in continuous variables, we came to characterize those with standard deviations. A bit of a mathematical statistical exercise to accomplish that, an extensive table. In fact, it's called an extension table, in order to get all of the columns that we needed to get the sums of the x's and do the divisions and get our mean for the values expressed in that table. But one of the things we saw there that was interesting is that just if we had no other information but the standard deviation and two distributions, and only the standard deviation from two distributions, no other information, and we saw that one standard deviation was larger than the other standard deviation, then we could make the inference that the standard deviation that is larger represents a wider distribution. The one with the smaller represents a narrower distribution. You get an illustration of that when you get to Chapter 5. In the opening of that chapter, there are figures 5.1 and 5.2. There, in Chapter 5, we're expressing the standard deviations in terms of the normal curve, the drawing of the curve and the vertical lines being the standard deviations. 1, 2, 3 positive standard deviations to the right, and 1, 2, 3 negative standard deviations to the left. It is a normal curve, 100% of the distribution from the high value to the low. Everything to the left is a negative. Remember, we're subtracting the mean from any of these, we get a negative. That's the negative side of the distribution, it's the positive side. This side is 50%, that side is 50%. So when we look at the, you notice when you look at the figure 5.1 and 5.2, you'll notice that one is a heaped curve and one is a more broadened out curve. They're both normal because they're symmetrical. They're bells. One's a peaked bell and one is a more broad bell. You'll notice that the standard deviations, for figure 5.1, the standard deviation is a 20, and the standard deviation for the one that's figure 5.2 is a 10. The figure for 5.2 is the space between the vertical bars, the vertical lines, is narrower. You can think of it as geography, if you like. If the geography between the two bars is narrower, then that means that it's a smaller standard deviation than, say, one where the space between the vertical bars of standard deviations is broader or wider. So you get for a standard deviation of 20, a more broad-based, rounded bell, and for the standard deviation of 10, you get one that's more heaped. Now, here we have, let's talk about why we want to do the z-scoring. There are a couple of reasons. You may just stay in the realm of descriptive statistics. Maybe you work for a community-based organization and you have 500 clients. And so maybe one of the things, and you score something, you score them on a scale of some sort of 0 to 100. And you know what the mean is, let's say, in that distribution of 0 to 100 for those 500 clients. But maybe you want to know what is the proportion that's scored between 63 and 68. You've got the standard deviations of your distribution, but you want to know where in this x-axis lies a particular value in that distribution of 500 cases that are scored between 0 and 100. The z-scoring allows you to find that. It allows you to find such things as, let's say, if your score was 99, how many people scored of that 500? What percentage scored between 99 and 78? What percentage scored above 99? What percentage scored all the way from 0 to 99? Any number. If there was a 48 here, what percentage scored between 48 and 99? These scores very practical kind of methodology for looking at distributions, or the distributions within a distribution, shall we say. And you can do three different things that are interesting here. One is you can get the proportion. We don't use proportions too much. I think we usually think about percentages, right? But you can get the proportion. That's what it begins with. Multiply that times 100, which you remember from Chapter 2, and you get a percentage. In this case, if this were 99, then this would tell us that about 3% of the distribution lies above 99. We also have probabilities here. We could say, if we were to take this value of the proportion, where this is 10, 100, 1,000, and 10,000, we could say then that 2 out of every 100 people in the distribution score 99 or above 99. So we've got the proportion above 99, we've got the percent above 99, and we've got the probability above 99. And of course, the same thing above 99 would work for whatever the probability of occurrence between 78 and 99, the proportion there, the percentage there, or any value here and there, or any values down here. Any two values of interest to you, one of them being the mean or two of them not being the mean, you can calculate out proportions, percentage, and probabilities. That's a pretty good idea. The other thing that makes it very interesting for us from an inferential standpoint, remember, even when we're doing inferential statistics, which we'll get more into next week, when we're doing statistics, we're doing descriptive statistics, we're doing explanatory bivariate statistics, and we're doing predictive multivariate statistics. And as we do that, since we can't take this route here, it's too expensive, prohibitively in terms of personnel and costs, we draw down a sample that's representative, which we'll talk about next week, and then we do the analysis on the sample to get our statistic. This is what we're after, some percentage or a rate or some descriptive value up here. What is up here? So we get the statistic, then we make the inference that had we gone this route, and we've talked about this before, the value we find here would have been pretty much what we would have found up here had we been able to go this way. Well, when we're doing the z-score, maybe we want to know, say this is our example here, maybe we're wanting to know what proportion in the population scores above 99. Maybe we've got a sample, and we're doing an analysis of a sample, imagining that to be an analysis of the population, which in fact it is. And so here then we would say that what we found in our sample, this being our sample, let me back up for a second. What we assume in terms of normalcy is that, and you'll see this in Chapter 6, as sample sizes go up, they take a more normal shape. as we go from 100 to 500 to 1,000, the distribution takes a more normal shape. And since the population, we're assuming, say, San Antonio is 1 million or something, if we've got a continuous variable, we don't ever see this so much, but we assume it also has a normal curve, right? So if we're doing our sample, we've got a sample size sufficient size where we've got something that approximates normal, then whatever we find to be here, we can infer would be what we would have found up here had we done this part. But we weren't able to do this, so we pulled down the sample. We do the analysis here. What we find here, just like we said, if we find the mean of this sample, we expect that to be a good estimate of what the mean would be had we up here, which is the parameter. If we were looking for the parameter, we found this mean, we would say by inference this is probably what we would have found had we gone that way. The same thing with z-scores. If you want to know something about the distribution between two values or between the mean and another value up here in the population, then what we find here, if, in this case, if this is our sample, if we find that 2.87% score above 99, we can make the inference that in the population that's likely to be the same situation. That up here in this one it would be approximately 2.9%. So it works both descriptively, purely descriptively, where you're not doing a sample and inferential statistics, but also works well in inferential when you're trying to figure out a distribution or estimate a distribution up here in the population. So it's a very practical statistical procedure, z-scoring. Now z-scores are standard deviations in a way. Here's an example. This is problem 5.6i. This is, I think, on your homework, where the mean is 78, the standard deviation is 11, and the x value of interest to us is 99. This is the z formula, xi minus x bar over s. Xi, of course, means all of the x's in the distribution. Instead of saying x1, x2, x3, x4, we just say xi. And then here we've got z equals 99 minus 78 over the standard deviation of 11, and that's 21 over 11. That's 1.90. So we get a z-score of 1.90. Now, what that means is that's 1.9 standard deviations to the right, because it's a positive value, 1.9 standard deviations to the right of the mean. So I've drawn a vertical red line to represent where 99 lies on this distribution. Here's 78. 99 is out here to the right, and there is the standard deviation, 1.9 standard deviations to the right is that vertical bar. That's the z-score. We say it's z-score instead of 1.9 standard deviations, although you can say it that way, to kind of help differentiate. You don't want to get lost too much in what is a z-score. A z-score is just another way of saying where on the distribution is that standard deviation, the standard deviation of that value of interest. It's not a standard deviation 1, it's not a standard deviation 2, it's a standard deviation 1.9 to the right of the mean. All right, then in order to accomplish this, we go to Appendix A in the textbook. So you want to do that. There's good illustrations in Chapter 5 how to do that. And since we're looking at the problem asks us to do the is above. Let me get over here real quick. Is here we go. Is above 99, then that means beyond 99 in the Appendix A. So we would go to column C. What is above or beyond 99? And go to column C, and we go, and for z-score 1.90, we see the C column says 0.0287. That tells us that that's the proportion above 99, the percentage above 99, the probability of people being out in 99. 2 out of every 100 in the distribution are above 99. If we wanted to, we could do the look at what the proportion is here. You look at column B in for 1.90, and it would give you the percentage or the proportion that lies between here and the z-score of 1.90. What proportion lies there? That's column B. Now we know that this is 100, right? Or all the way across from the right-hand side of the mean is 50 and the left-hand side of the mean is 50. So if this is, say, 3%, then we know we've got about 47% between the mean and 99. So we get that information pretty quickly using Appendix A. Now, I just wanted to point out a couple of things before I close. There are a couple of procedures that you want to think about and be careful about, actually, when you're doing the z-scoring. One is where you've got z-scores on one z-score is on the right-hand side of the mean and one is on the left-hand side of the mean. Healey's got that described and a table on what the steps for doing that. So I think it's laid out pretty clear, but I just wanted to point it out. If you've got two z-scores and one is on the right-hand side of the mean and one is on the left-hand side of the mean, then you take the two column B's, the column B for the one on the right-hand side to the mean and column B for the one on the left-hand side of the mean, and you simply sum those up, and that gives you the total amount of proportion, percentage, or probability between those two z-scores. If, on the other hand, your two z-scores are on the same side of the mean, whether on the left-hand side or the right-hand side, then if you'll subtract one z-score from the other z-score. So you would subtract it would be follow the instructions of subtracting one z-score from the other. Z-scores on either side, two z-scores on either side of the mean are subtracted. Z-scores that cross the mean are added. And I think that's all that I wanted to say. I wanted to highlight again proportions, percent, and probabilities of what we gain from doing this. And not only is it good descriptively, if you've got your 500, let's say, clients in a community-based organization, to look at distributions within the distribution of those 500 clients. It's also good inferential if you're in inferential statistic mode. Whatever you find in your statistic in the way of z-scoring, you can assume that the inference would, if you've got a good sample size, that you've got an accurate estimation of that same distribution up here in the normal curve, hypothetical normal curve of the population. So that's Chapter 5, and talk to you next week about